just waiting for the thumbs up, guys. I think we'll be... No, maybe do one more minute. I think that's a thumbs up. Okay. Hello. I'm going to proceed as if it was a thumbs up. Welcome, everybody, to the Ice World Festival. Welcome specifically to the talks that we're doing. My name's Ed. You don't have to worry about me. I'm actually an astronomer, so I am going to be listening in just as intently as you are, I'm sure. But I'm hosting things for today, and it's going to be pretty straightforward. We'll be meeting our speakers in just a second. But before we do that, there's just one or two little things. First of all, we're also going, we're being sort of broadcast to YouTube, and we're also going out to various screens across the site. So as well as the talk, we're also going to do a bit of a Q&A session. And in that, don't worry, I'm going to come around with the mic, and I will repeat your question. You don't have to shout, you don't have to try and project or anything like that. I'm going to, whatever you do, I'm going to repeat the question anyway, because I want to make sure it's picked up by everybody. So that's one thing. It's a bit of a sort of unnatural rhythm, but we'll get through it, I'm sure. The other thing is, this might seem slightly off topic, if you want to take part in the Penguin Parade, that's happening at 4. So if you want to dress up like a penguin, there's the ability to do that, or you might have your own costume anyway. I'm not here to judge. But at 4 o'clock, they're all going to march over, and the captain is actually going to honk the horn of the ship. I don't know if you call it a horn on a ship, but you know that's all happening. So that at 4, so I just want to mention that. And as well as that, if perhaps you've just come to one of these lectures but you haven't seen the exhibits, I do want to encourage you to go and take a look at the BAS exhibits that are on the Great Map and indeed in the learning spaces across the site, because there's some amazing stuff. However, I won't take up too much more of your time. I'm going to introduce our speakers. I'm going to read it because I want to make sure I get it right. We have 2 PhD students with us with the British Antarctic Survey. We've got Dorothea Moser and Bryony. And they are going to be talking about their efforts, their work to understand the past, present and future of climate change in Antarctica. And they're going to be explaining the different tools that they use unlocking stories from the ice itself. So if you can give them a big round of applause, and then we'll jump into it.
Thank you very much, and yes, welcome to our talk. I hope you've been enjoying your time at the Ice Worlds Festival. And we're really excited today to be speaking to you about all of our work as glaciologists at the British Antarctic Survey. I mainly study the ice from satellites, so that's me over there on the left, and
I'm Dorothea, and I study ice cores to reconstruct the climate of the past. And maybe to start with, it's good to have a short reminder, what are we dealing with? So what are the Arctic and the Antarctic? The Arctic is where the bear is. That's the literal meaning of it. But in general, the polar regions are near the North and the South Pole. And while the Arctic is the region of an ocean surrounded by several continents, and it's covered by sea ice, it's the opposite way around for the Antarctic. It's a continent covered by ice and then surrounded by the Southern Ocean. And the two of us are dealing with the Antarctic. The special thing about it is that it's the highest, the coldest, the driest, and the windiest continent of this Earth. It's a special place to work in, and it's incredibly important, and that's something Bryony is going to mention to us now.
yes, so the Antarctic holds the largest ice sheet in the world, and along with all of the ice shelves that fringe the continent and the sea ice, that covers 28 million square kilometers of ice, which is pretty huge. And if that was to all melt, which warming temperatures from climate change is kind of threatening, it could raise global sea levels by up to 58 meters, which is like 22 flights of stairs. And if we move on to the next slide. And so how would this affect us here in London? I hope you recognise is the Thames, and the red pointer shows where we are here in Greenwich. And with data modelled by NASA, we can have a look at how different rates of sea level rise would kind of affect us here. So this is showing with 2 meters of sea level rise, which is one of the upper predictions that we could reach by the end of this century, according to the IPCC. And we see a lot of kind of extra flooding along the banks of the Thames and in other small pockets of London, which is it's really highly populated, obviously, would cause lots of problems. If we move to 5 meters, we're getting a lot more inundation. And 10 meters, again, London essentially becomes a river. Greenwich, though, seems to still be okay. But when we go to 60 metres, London's gone, basically. And this isn't going to happen in our lifetimes or even kind of thousands of years, but just to give an idea of the scale of the amount of ice that's down in Antarctica. And this is why we're really interested in studying it, so we can better predict kind of how quickly sea levels are going to rise around the world.
So this is sea level, but why am I interested in ice of Antarctica? First of all, it all started with snowflakes, at least for me personally. If you have a look at these images, in my opinion, snowflakes are incredibly beautiful. And they're not just beautiful, they're unique. If we were to consider my favorite fact about snowflakes, every single snowflake in the entire universe is unique. And that's quite mind-blowing, especially when you're in an environment like this, fully glaciarized, covered by snowflakes, thinking about not only the beauty, their uniqueness, but also their informational value. Because each snowflake carries information about the environment in which it was developed and where it falls. And that's what I'm interested in as an ice core scientist. We need the layers of those snowflakes, and we're drilling into glaciarized surfaces, retrieving records, ice cores from those sites and their environmental history. So how does that actually work? First of all, we have to get into the field, and that's either with our new ship, Sir David Attenborough, that's currently here in London, or using airplanes, or being deployed from the helideck by a helicopter to our smaller sites on the islands. But then we're staying in the field, and that's where we're confronted with the forces of nature, either in a tent or in a station like Halley. And that's where we carry out our fieldwork then. You're going to be able to see some of that equipment in the exhibition, so check that out. But when we then drill an ice core, what does that actually look like? I've got a short video for you, and we're going to observe the drill go down the borehole. What's a drill? It's an empty barrel, a masterpiece of engineering, to be honest, and it's let down on a long wire to retrieve ice core samples by grinding its way downward and holding it with some sharp knives in that barrel. So it takes a lot of patience letting that barrel down into the hole. The deeper we get, the more time it takes. And then we bring it back up when the barrel is filled with ice. So we're opening the chasm, waiting for it to return, handling it carefully because both these devices and the samples are rare and expensive. And then, this is the drilling tent from outside. We lower the drill head so that we can empty the barrel. And then we pull it to the side, decontaminate the rim, remove ice chips that have accumulated outside during the drilling process, and push out the sample really carefully. The most important rule in ice core science is never confuse top and bottom, because that's going to mess up your entire story. And when we're done with that, we're putting it all in boxes and bring it back to the lab, because that's where the analyses are made. So in the lab, it's not any lab, it's at -25, because otherwise our samples would melt away. And we've got various analyses, anything from structural measurements to chemical measurements. I like the variety of measurements and approaches that we can apply to ice cores very personally. And then we've got the ice. What information can we extract from it? First of all, there's the ice itself. You can see an X-ray scan of it right here. And you can see some layers. We can see that as a record of snowfall events, individual storms maybe, and they are distinct in their appearance. So we've got a record of that. And the composition of the snow itself is also an indicator of past air temperatures. Then we've got impurities. It's not purely water, but everything it picks up on its way to Antarctica, we're going to see that in our record. And that can be anything from volcanic ash to pollen, And that's going to be an indicator of maybe atmospheric circulation. Where did the winds come from? What did it pick up? And also chemical impurities can be a tracer of the sea ice extent and its variability around Antarctica. Last but not least, there's the air of ice cores. And that's maybe the specialty, because it's direct evidence of the atmospheric composition of the past. You're welcome to have a look at that at the ice core stand in the exhibition above. But in my opinion, that's the best part. And it's very unique because other records of the environment don't have that direct evidence. By combining all these different aspects of ice cores, we are able to reconstruct the climate of the past. And that is possible over the last 800,000 years. So that's a long history. And that is actually what puts our current observations of CO2 level in context. Over the last 800,000 years, CO2 levels in ice cores and in our atmosphere have never been above 300 ppm. Now, we're faced with more than 400. That's a lot. Now, to give you an impression of what melting causes to ice, you can see air bubbles pop in from these ice core samples. And while it might be beautiful to look at right here, melting is an issue for ice cores. And that's something I personally am working with. Which information are still recorded in these ice cores? That's a question that needs to be resolved for ice core science in a warming climate. So I'm using these more bubble-free layers when the ice core has molten and refrozen in a certain section and try to reconstruct what it can actually be used for. And now we're going to transition to a bit more of a remote approach to studying Antarctica.
Do you want to give me this? Yes, thank you. So yes, while Dorothea studies ice cores to reconstruct the past climate, I take a slightly different approach in my research of the ice sheet. So I use this network of Earth observation satellites that we have that orbit our planet every day. There are over 650 Earth observation satellites currently in orbit, and they all kind of measure different things with different parts of the electromagnetic spectrum. And some of them kind of work like a giant camera, taking pictures like you see on Google Earth. Others have more specialized instruments on board that transmit kind of radar or lasers down to Earth and measure what bounces back. And from this, we can measure a whole range of properties of the ice sheet. And this has kind of revolutionized polar science because it means that we can collect data over the whole continental scale without having to go directly in the field necessarily, which is, a very expensive, it's a very inaccessible place, and not to mention very cold. So I'm just going to show a couple of the cool applications of satellite data to the ice sheet today. So firstly, Dorothea was talking about melting layers in her ice cores. And obviously this happens when temperatures get above 0 degrees consistently. And we can see with satellites what this melt looks like on the surface of the ice in real time. So this picture here shows an example of kind of these surface lakes that pooled on the George VI ice shelf in Antarctica. And this is taken from a plane, so we can see them really clearly here. But obviously it's really kind of inefficient to send a plane around the whole of Antarctica. It's far too large to do that. So we can turn to satellites like the European Space Agency's Sentinel-2 to get a kind of bigger picture. And this is the sort of images we get from the satellite. Now this is an image from the same ice shelf as before, and it was taken on a day in January 2020, so just before COVID struck. And it was on a 32-year record melt event. And you can see it's a really extensive formation of these ponds all over the ice shelf. And just for an idea of scale, this is about 30 by 30 kilometers. So each of these bigger lakes that you see here are 5 kilometers wide each, which just gives an idea of the scale of these features and why satellites is really important to be able to kind of measure them on this scale. And surface meltwater production is predicted to double by 2050 in Antarctica, and so it's going to start happening in regions that we never expected it to, or that we never thought really got above 0 degrees. And so satellites are going to be really critical in tracking this. So other than showing that the temperature is rising, another reason why we're really interested in these melt features is that they've been linked to the breakup of ice shelves, which are these really dynamically important regions of ice that fringe the continent. And they kind of act as giant buttresses to hold back the flow of glaciers from inland into the ocean. And so this process has kind of dramatically caused a breakup of an ice shelf in Larsen B in 2002. And I'm just going to play a time-lapse of satellite images that we saw. And the scientists were kind of looked in amazement at these images as the entire ice shelf collapsed over the course of a single month. And this is 3,000 square kilometers of ice. So that's about double the size of Greater London, all just gone in the course of a single month. And this followed a series of kind of warmer summers, especially the 2002 summer was exceptionally warm. And it caused all this melt that you can see in the first images that appear, the blue dots, all these melt ponds. And they kind of acted as giant wedges where they like deepened the crevasses and kind of splintered the ice shelf apart. And the ice that's lost as icebergs into the ocean, this isn't directly contributing to sea level rise, but what scientists could kind of measure with satellites was that these glaciers, all to the left of the image, that are flowing into the ice shelf, suddenly sped up dramatically after this ice shelf collapsed, up to 300% speed ups. And it increased the total mass of ice that was being lost into the ocean every year from about 4 gigatons per year before this collapse to 40 gigatons per year after. So that's so much more ice that's being lost into the ocean and contributing to sea level rise. And now some of the ways that we measure this changing ice speed. We essentially can take repeated images over the same area and then track certain features like surface debris or big crevasses and see how much it's moved between images so we can work out the speed. But with a lot of satellite data, the optical data, like in the previous images, if there's ever any clouds, which happens a lot in Antarctica, or during the winter where it's 24 hours of darkness, you can't see anything. So we turn to these radar satellites, which use longer wavelengths. They can see through clouds, and they don't need the sun to be there. And it allows us to measure how fast the ice is flowing all around Antarctica. And so this is a little time-lapse animation of radar images we get over Pine Island Glacier. And you can see the ice traveling like a giant river to the ocean where it's carving off these big icebergs. And this glacier in particular was found to have sped up by 42% since the 90s. Which is quite tremendous, and it's draining a lot of the ice sheet, so this is quite worrying. But if we're to kind of fully understand the relationship between ice loss and sea level rise, we don't just need to know how fast the ice is moving, but also how thick the ice there is. And so we turn to another range of satellites called altimeters. And one of these is ISAT-2, which is shown here, and it's what I am lucky enough to use in my research. And it essentially sends down lasers to Earth and measures how fast it takes for the individual laser pulses to go from the satellite down to Earth and back again. And we can measure the Earth elevation of the ice to within 4 millimeters, which I think is pretty spectacular considering this satellite is flying around the Earth over 480 kilometers above us. And so if we can do this over the continental scale, over many, many years, we can start to see where the ice is thinning or thickening and produce kind of maps like this. So this is showing mass loss from Antarctica between 2003 and 2019. All the red areas are where we're losing a lot of mass, mainly caused by warming oceans and ice shelf collapse. And there are lots of areas in blue where it's a slight thickening that's actually a short-term effect because there's been increased precipitation as a result of many factors to do with climate change. And this is really, really critical information for us to be able to predict the future mass loss that we're going to see and how quickly it's going to contribute to sea level rise in the future. So, yes, satellites I hope have shown, can kind of give us the whole three-dimensional picture of ice in Antarctica. So it covers the whole spatial area and also gives us that third dimension of thickness. But when it comes to the fourth dimension of time, we're a little bit limited because we only have satellites going back to about 40 or 50 years ago. So this is where we kind of turn to ice cores and to kind of put these changes, present-day changes that we're seeing with satellites in the context of longer climate history. And so it just kind of highlights how complementary these two different approaches are to studying the Antarctic ice sheet.
And to wrap it off, we're on the eve of COP26. I hope we've shown you that what happens in Antarctica is not somewhere happening remotely, but that it's all connected. And that is quite interesting to work on this subject. But if we see the future of the Antarctic ice sheet, and we see our choice between high emissions and low emissions, and we see our politicians making decisions about our future, it's important to know that it's our choice how the future of Antarctica and of our planet is going to develop. And while our politicians may be discussing, we can't negotiate with a melting point of ice. Thank you for your attention.
Thank you so much. That was absolutely brilliant. Folks, we do have just a few minutes for some questions, if you have any. Don't be shy. But remember, I'm going to come round and I will repeat anything you have to say. Bear with me. That's a good question. What's the deepest ice core that you've drilled out?
So you may all have a guess, but it's several kilometers. So more than 3.5, if I am not mistaken, but that's my best guess. Maybe you can go back to the slide that we had. So yeah, the ice thickness is more than 4 kilometers, but our oldest records, or our deepest records, are more than 3.5 over there, and maybe close to 4 on that slide. So for Vostok and the Waste Divide. Yes.
Yeah. So does that mean that the age of the ice is different at different depths, at different parts of the thing? Because that says 400,000
Yes.
years there, and then it says 68,000 years over there.
That may be a bit confusing, wouldn't it?
Yeah.
Sorry, I'm just going to repeat just for everybody on the screens. There doesn't seem to be a correlation necessarily between the depth of the ice and the age of the samples. So different depths, different ages in different locations.
Yeah. So, of course, the age is not only depending on the depth, but it depends on how much snow is falling per year. Because the more snow that is falling during 1 year, the thicker the annual layer, and the fewer years you're going to have in 1 meter of ice at the surface. So there's a compression with age and with burial if new years are layered on top of each other. But if there's a site on the coast that experiences a lot of accumulation, the resolution of the ice core will be higher because the annual layers are thicker, but it's not going to go that far in time. While an ice core that has very thin annual layers, a bit less of a resolution per year, it might go back further in time. And another factor that plays a role is, of course, the flow of the ice sheet. If at a certain point the ice is flowing, it might, or it's melting at the bottom, we might lose something of that oldest ice at the bottom. Currently, there's a project called Oldest Ice, and it's aiming for an ice core that covers more than 1 million years. So that's a bit of that context. And they're especially interested in exactly what you asked. Where do we find the best resolution, but also where do we find that oldest ice?
Oh, we do have one down the front. Yeah. Do you store the cores? Do you store all of the cores once you've finished?
It's quite a bit of work, and it takes a lot of storage. Yes, we do store the cores. We cut them in pieces, and parts of them are melted when we've dealt with them. But we try to keep an archive of every site that we have so that we can maybe remeasure certain sections in the future when measurement approaches have changed or improved. And we've got several kilometers of ice stored in large freezers at -40 around the world. So all our collaborators are joining forces to keep such a large storage archive of ice cores, yeah.
We've got a few more. I'm going to go up to the back, and then, don't worry, I'll come back for more.
Sorry, it's a bit complicated question. Like, when you're studying ice cores, is it like morphological studies across volcanic eruption? If it's protected in one type of ice core and not in the
going to try and parse that, I think. So it's about whether, you know, we're taking multiple samples, but you might observe something in one sample but not in another. And so when you're studying them, because you can only study a limited number, is there a danger there that you're missing something?
Yeah, there is a danger to missing certain information, depending on the winds. I mean, we do know if the wind is coming from the west, it will carry that information from the west towards that site. But if there were easterly winds in a different area, we would capture different information. So a crucial part of ice core science is to understand at which site we get the winds from which direction, which environmental factors are feeding our chemical records and what we see in our ice at that site. So we do need that regional understanding of the environment to actually understand our record. And it could be that certain volcanic signals are captured in one record and not in the other. When it comes to polar ice cores, we tend to get just the largest eruptions that are in the tropics, because smaller eruptions would not be captured because the wind is not strong enough to carry it that far. But a typical eruption that is captured in ice cores is the Pinatubo eruption in 1991. So we use that as an absolute time marker because we know that it happened and we can see it in different ice cores, either chemically in the sulfates or as literal ash shards that we can sample and look at under the microscope.
How many years will it take for it to be meeting level?
Okay, so the question is, how long will it take for 2 meters worth of sea level rise?
Yeah, so that's a big question. So the IPCC currently predict that by 2100, I think sea levels will rise between 1 and 2 meters, probably closer to 1 meter. But a big question is what happens to the Antarctic ice, and whether there's a process called marine ice sheet instability, where a lot of West Antarctica is grounded below sea level, and if it starts to retreat, it could kind of fall into a very unstable pattern of retreat. And if that happens, a lot of ice will be lost, and then we'll be closer to the 2 meters. So these are big questions for glaciologists, and we're trying to work out how quickly it will happen. But yeah, there's big kind of errors on the estimates, but we know it's rising.
If I understood you correctly, you said you could measure the depth of the ice or position to within 4 millimeters.
Yes.
That seems incredibly accurate. But what do you use as a reference point?
Yes, so we do kind of validation studies. So there was a big mission that went down to the South Pole, and they kind of drove around with a skidoo with a GPS and kind of measured the exact height that they with a GPS, and then they could validate the measurements from the satellites to that. But with ISAT-2, it's very precise, and it will bounce off the surface layer of anything. And there's been lots of like lab tests that have kind of confirmed this with the instrument before it went up into space. Yeah, but it's pretty remarkable.
If I can just chime in, you can also calibrate lots of satellites using salt flats, particularly in South America, because they're basically completely level, and you can bounce signals straight off them and get your calibration while you're in orbit.
They put kind of big corner reflectors on the ice as well, so they know when the satellite's going over it, and they'll get a really strong return from one of these corner reflectors, and that's another thing they use.
I think we've got time for one or two more. Okay, so should we be worried about things that are potentially lurking within the ice cores? We do hear on the news about permafrost melting and potentially releasing viruses. Is this an issue with ice cores in the Antarctic?
So Antarctica is the remotest place on Earth, and it is probably also the cleanest place on Earth. And that is because it's that remote, and I can't imagine, or I don't know about any viruses that are captured in that ice, because it's Antarctic ice and there are no indigenous people who may have suffered from viruses in that region. So everything that we encounter down there should be fairly recent, since we've explored the Antarctic. But when it comes to permafrost, we've come across some incidents in Lapland, in Sweden, where there have been permafrost graveyards thawing and viruses being released that were buried in that graveyard. So permafrost melting is not just an issue when it comes to the emission of methane, which in my opinion is maybe the major one, but it could also release viruses.
Maybe a Hollywood sort of horror film, you know. Okay, we've got time for one last one, so I'll give it to you, sir.
Can I ask what you think is the most interesting or alarming thing detected in Antarctica?
What's the most interesting or alarming thing you've discovered with an ice cores?
I think it probably feeds into something we've both observed, both in ice cores and from remote sensing, and it's the increase in melting. I, as an ice core scientist, see more and more of these features, melt layers, these bubble-free layers, and ice core scientists have tried to avoid studying them by going to places that were not affected by surface melting in Antarctica. But now there's simply no way around it, because the coastal regions are the ones changing most quickly, and they're the ones draining ice into the sea and constraining mass loss. So we need to study these sites, but they're affected by surface melting, and I think that is probably the most remarkable thing, seeing that increase in those features, and at the same time being confronted with a lack of knowledge about that. And you've seen that change of mass loss from space.
Yeah, the statistics of how fast things are how quickly things are speeding up or thinning is quite concerning. Like, some of these regions are losing kind of 10 meters of surface height every year, which is staggering, really. So it can be quite depressing when you're looking at these on a daily basis. But hopefully our science can help to understand and help humans mitigate the impacts around the world. So it's quite rewarding.
Well, it's a sobering end, perhaps, but I'm afraid to say, folks, although our speakers are brilliant and we would quiz them all day, I'm sure, but we do have to put a pause on it there. So first of all, can we say thank you and a round of applause once again for our speakers, Bryony and Dorothea. There are a few more talks going on, and I do believe you guys are going back to the exhibits, and so if you want to ask more questions, please do check out the exhibits, of course. We've got a couple more talks, as I say. We've got 2 more remaining for the Saturday sessions. Remember the Penguin Parade, don't forget that, if you're so inclined. But thank you very much for coming, everybody, and we hope you enjoy the rest of your day here and the rest of the Ice Worlds Festival. Thank you.